This is number 110, part A in chapter 15. It looks at polyprotic acids, and it looks at a solution that is 0.125 molar in carbonic acid, and we want to solve for our H3O plus concentration, and we also want to solve for our pH. So we have a solution. Notice we have two hydrogens written first. That's indicating it's a diprotic acid. And so we should have two equilibrium steps for each loss of each acidic proton. And as such, we should have two Kas. And we actually do. We have to go and look these up in a table. In Ka1, we get 4.3 times 10 to the negative 7th. And if we look up our Ka2, we get a value of 5.6 times 10 to the negative 11. So we want to use our two Kas to solve for our pH and our H3O plus. Now the first thing we can do is we can assume that H3O plus and pH are resultant from the first step, or Ka1. That's because of the drastic difference we observe in the Kas. We have a Ka1 of 10 to the negative 7th for the first proton. We have 10 to the negative 11 for the second. That is very significant, and so what we'll find is that because of that significant differences in Ka, that really the H3O plus concentration and pH is solely resultant from the change in the first step, or resulted from that first Ka. So what we're going to do is we're going to actually prove that in this question. It's not really asking that, but we're going to prove that, and first we're going to solve for these guys using the first step, and then we will go further and look at the actual second step and see how that changes our concentrations. And so if we're considering the equilibria that exist, we have to consider the first step involving the loss of a proton to water to generate H3O plus and bicarbonate anion. From that we can deduce an ice table showing each of the aqueous entities that are changing in concentration. We have an initial, a change, and an equilibrium. 0.125 molar for our carbonic acid, 0 for our products, which tells us the direction of the equilibrium change, and then gives us our equilibrium concentrations with respect to X, or with respect to that change. So our Ka1 would be equal to our products over our reactants. And so our Ka, the 4.3 times 10 to the negative 7th, would equal x squared over 0.125 minus x. We can simplify this. Since Ka is small, we can say that the change relative to an initial starting material concentration would be negligible. And so we can say the x in the denominator is going to go to 0 as a result. And when we simplify, we get the Ka equal to x squared over 0.125. So we do some manipulation here. We would get our x squared equal to 5.375 times 10 to the negative 8th, or x equal to 2.318 times 10 to the negative 4th. So that's x, And remember, X is going to be equal to our H3O plus concentration as well as our HCO3 minus concentration. And we should also check that that assumption is valid. Kind of running out of space here, so I'm going to have to erase some of this. Derivation. In order to check, we would take our 0.125 minus our X over 0.125 times 100. And remember, we want that to be greater than or equal to 95%. And so if we take and now substitute in minus that change of 2.318 times 10 to the negative fourth over 0.125 times 100, you get 99%. So this is a good assumption. So this X is a good value for us. So if that is X, that's our H3O plus, and from that we can actually now get the pH as well. And so to now answer the question, since our X is equal to 2.318, that is our H3O plus concentration. And remember, that was also equal to our bicarbonate concentration as well, right? And so not only is it equal to H3O plus, it's also equal to our bicarbonate as well. And so that answers the first question as far as our H3O plus concentration. The pH then would simply be the negative log of that concentration, 2.318 times 10 to the negative fourth. And our pH then is equal to 3.63. So that's from the first step. Remember, again, because of our assumptions, A, that X is small, but really the more important one is that -7 to -11th, we have such a drastic difference in those Kas that really it's only this first one that we have to consider in the amount of H3O plus and our pH. Let's go one step further and actually prove that and look at the actual second step. And so we look at the second step, we have now going to begin with our bicarbonate. That was the product of the first equilibrium. And so now it's going to be the starting material of the second. It's also going to donate a proton and then form carbonate. And so that is the equilibrium that exists for the second step. And so that would be our second Ka, or Ka2, which would be, again, our products over our reactants. And from that we can generate an ice table. But now what to fill in for our ice table? What we have to realize is that since this is the second step, that the initial conditions that we have are going to be a resultant of the first step. And so this is where it becomes important to realize that that change for H3O plus is equal to the bicarbonate. And so really we have two initial concentrations because these are the concentrations that we arrived at the equilibrium for the first step. As such, they are now the initial concentrations for the second equilibrium step. So we would have our 2.318 times 10 to the negative fourth and our 2.318 times 10 to the negative fourth, and then 0 for our carbonate concentration, The 0 is telling you which way the direction must go. And so we end up with equilibrium concentrations of 2.318 times 10 to the negative 4th minus x, 2.318 times 10 to the negative 4th plus x, and then also x at the end. So just like before, now we're going to plug these guys back into our Ka2, and that Ka2 is equal to 5.6 times 10 to the negative 11th, which would equal our 2.318 times 10 to the negative 4th plus x times x, all over our 2.318 times 10 to the negative 4th minus x. So as you can see, we're getting kind of complicated here, but again, our Ka is really, really small, so that means starting materials are going to be favored. So that means that that change relative to our starting material concentration is still going to be small. If it was small for the first Ka, it's definitely going to be small for the second, again due to the difference in those Kas. But if x is small relative to this concentration, then it's also by default going to be small relative to that concentration. And so we can say that both of those are actually going to go to 0. And so I need to make a little bit more room. If we come over to here, that means that our 5.6 times 10 to the negative 11th is equal to 2.318 times 10 to the negative 4th times x over 2.318 times 10 to the negative 4th. These guys are going to cancel. The numerator and the denominator, and so that means our x, which is going to be equal to the concentration of carbonate, is equal to 5.6 times 10 to the negative 11th. So from this we can actually figure out now all the concentrations that actually exist in this solution. And so to begin, I'm just going to make a little bit more room here. Right, and so we figured out that from the first step, our H3O plus concentration, right, which was equal to our bicarbonate concentration, was equal to that 2.318 times 10 to the negative 4th from the first step. Let's see how now that's changed with the second step. And so from the second step, we found that the concentration of carbonate was equal to 5.6 times 10 to the negative 11th. Now let's see how that change, right, because remember that's x, how that change impacts our other concentrations, right? For our H3O plus, that was equal to our 2.318 times 10 to the negative 4th plus x, right? Or 2.318 times 10 to the negative 4th plus 5.6 times 10 to the negative 11th. That means our H3O plus concentration would then equal 2.318 times 10 to the negative 4th. Notice that there's no change in looking at the first and the second reaction combined with the H3O plus. So that's why we could say that the H3O plus concentration is really a sole result of the first step, as well as the pH being a sole result from the first step. We can then go further and solve our other concentrations. Again, you'll notice that they won't change much. Our bicarbonate concentration was 2.318 times 10 to the negative 4th plus x, minus x, or 2.318 times 10 to the negative 4th minus the 5.6 times 10 to the negative 11th, which gives us our bicarbonate concentration to be equal to 2.317 times 10 to the negative 4th. And then lastly, we could also figure out the concentration of the carbonic acid originally, right, which remember was 0.125 minus X from the first step, or 0.125 minus the 2.318 times 10 to the negative 4th, to then give us our carbonic acid concentration to be equal to 0.124 molar. And so while it didn't ask it, we can actually solve for all the concentrations that exist in equilibrium, even though it's a two-step process. But again, please remember, if you're just solving for pH or concentration of H3O+, take in mind the differences in the Kas. If there is a drastic difference, like in this case, 10 to the 5th difference, that means you will not see any change in the amount of H3O+ you make from the first step to the amount you would make from the second step. No change. So that means we can just solve our H3O+ and our pH from the first Ka. That is number 110A from chapter 15.